The first drone that truly changes the world will not impress us by flying higher, faster, or carrying a better camera. It will impress us by doing something much harder, refusing to fly when the mission is unsafe. That is the line between a machine that moves through the air and a machine that deserves permission to operate above people, roads, hospitals, factories, farms, borders, and cities. The future of drone engineering is not about building flying gadgets. It is about building aerial systems that can be trusted with responsibility. Most drones today are still treated like tools. Someone launches them, someone watches them, someone controls them, someone takes the risk. But the next generation of drones will not survive on remote control. They will have to work in complex airspace, beyond visual line of sight, around helicopters, power lines, birds, cranes, wind, rain, weak GPS, cyber threats, and unpredictable human behavior. In other words, the future drone will not be judged inside a clean demo. It will be judged in the ugly, changing, dangerous real world. And that is where many people misunderstand the future. They think the next big drone breakthrough is one magical aircraft, longer battery, better camera, stronger motor. But the real future is not one feature. It is a complete engineering stack. The drone needs a brain, senses, energy discipline, airspace awareness, cybersecurity, explainability, and the humility to fail safely. The most important word in future drone engineering is not speed, it is autonomy. But autonomy does not mean the drone follows a route. That is only automation. True autonomy means the drone understands the mission, reads the environment, detects risk, adapts its route, protects people, and knows when to stop. A drone that follows GPS blindly is not intelligent. A drone that sees a construction crane where the map said empty sky, calculates the risk, reroutes, reports the decision, and continues safely is closer to what the future demands. This is why artificial intelligence will become the central nervous system of drones, but not the kind of AI that depends completely on the cloud. A drone cannot wait for a server to think when it is flying toward a wire, a tree, or a building edge. The intelligence must move on board. Edge AI will allow drones to process video, radar, thermal data, sound, motion, and location directly inside the aircraft. The future drone will not simply capture information. It will interpret information while flying. But intelligence without perception is blindness with confidence. That is dangerous. Next-generation drones need better ways to sense the world. Normal cameras are useful, but they can struggle with glare, darkness, smoke, fast motion, and sudden changes in light. This is why advanced research is exploring event-based vision, a camera approach that reacts to changes in the scene instead of recording full frames like a traditional camera. For fast-moving drones, that can mean lower latency and faster obstacle detection. In simple words, the drone does not just look, it reacts. Still, no single sensor is enough. The drone of the future will combine many senses: cameras for detail, thermal imaging for heat, radar for difficult weather, LiDAR for depth, inertial sensors for movement, barometers for altitude, and navigation systems for position. The real power is sensor fusion. The drone must take imperfect signals and turn them into one reliable understanding of reality. If GPS weakens, vision helps. If the camera is blinded by smoke, thermal or radar helps. If wind pushes the drone sideways, the flight controller reacts instantly. Safety comes from layers, not from one heroic sensor. The next major challenge is energy. This is the unglamorous problem that decides whether drone dreams become real businesses. A drone can have brilliant AI, but if it can only work for 10 minutes, its usefulness is limited. Batteries affect everything: range, payload, endurance, stability, cost, and mission design. Future drones need better batteries, lighter materials, smarter power management, efficient motors, aerodynamic bodies, and in some cases, hybrid or hydrogen systems for longer missions. Engineering is not fantasy. Every gram matters. Every watt matters. Every minute in the air must justify itself. That is why the future will not be dominated by one drone shape. A quadcopter is excellent for hovering and precision landing, but it burns energy. A fixed-wing drone can travel farther, but it needs more room to operate. VTOL drones, which take off vertically and then fly like airplanes, may become critical for long-range missions. The point is simple. The mission must design the drone. Medical delivery, bridge inspection, disaster mapping, farm monitoring, warehouse inventory, and offshore wind inspection do not need the same aircraft. The best drone companies will stop asking, "How advanced is our drone?" and start asking, "What problem does this aircraft solve better than any other option?" Airspace is the next battlefield of engineering. A few drones in the sky are easy to manage. Thousands are not. If drones are going to deliver medicine, inspect infrastructure, respond to emergencies, and fly beyond visual line of sight, they need more than permission. They need traffic coordination. NASA and the FAA have worked on UAS traffic management, known as UTM, to support low-altitude drone operations where traditional air traffic control does not normally manage every aircraft. The FAA's BV loss direction shows the same reality. Drones must be able to operate safely when the pilot cannot directly see them. In Europe, EASA's U-Space framework is designed to help drones and crewed aviation share airspace more safely and efficiently. This changes the identity of the drone. It is no longer just an aircraft. It becomes a connected participant in a digital airspace system. It must know where it is allowed to fly, who else is nearby, what restrictions are active, when weather changes, and how to communicate its intent. The drone future is not only about machines in the sky. It is about invisible infrastructure, digital corridors, identity systems, geofencing, remote identification, real-time risk data, and coordination between operators, regulators, and service providers. But connection creates another danger: cybersecurity. A drone that depends on communication can be attacked through communication. GPS can be spoofed, control links can be jammed, software can be compromised, data can be stolen. A drone carrying a camera, medical payload, or industrial sensor is not just a flying object. It is a moving data system. Future drones must be engineered like aircraft and protected like computers. Secure communication, encrypted data, authentication, tamper resistance, and intrusion detection will become as important as motors and propellers. Then comes the issue nobody wants to face until something goes wrong: failure. Serious drone engineering must assume failure from the beginning. Motors fail, batteries degrade, sensors lie, maps become outdated, weather changes, operators make mistakes, AI models misread situations. The future drone cannot be designed around the fantasy that everything works perfectly. It must be designed around the expectation that something will break. That means redundancy. It means backup sensors. It means emergency landing logic. It means return-to-home systems that are smarter than fly back in a straight line. It means parachutes for certain missions. It means health monitoring inside the aircraft. It means the drone can detect a dangerous vibration before a motor fails completely. It means graceful degradation. When one capability is lost, the drone reduces risk instead of collapsing into chaos. A trustworthy drone is not one that never fails. It is one that fails intelligently. And now we reach one of the most important ideas: explainable AI. If a drone changes course, denies a mission, lands early, or avoids an area, humans need to know why. Regulators need evidence. Operators need logs. Insurance companies need accountability. Engineers need data to improve systems. The public needs confidence. A black box flying robot will not earn trust. Future drones must be able to show what they saw, what risk they calculated, what rule they followed, and why they made the decision. The flight log of the future will not just record location and speed, it will record reasoning. This is also why drone swarms are both exciting and dangerous. A swarm can map a disaster zone faster than one aircraft. It can inspect large infrastructure, search wide areas, support firefighting, or monitor borders. But a swarm is not just many drones flying together. It is a coordination problem. The drones must divide tasks, avoid each other, share information, recover from individual failures, and avoid overwhelming the human operator. The goal is not to turn one human into an exhausted controller of 50 machines. The goal is to let one human supervise intelligent systems that reduce workload. The next generation of drones must also be quieter. This sounds small, but it is not. Public acceptance can kill a technology. If delivery drones make neighborhoods sound like mechanical insects all day, people will reject them. Noise engineering, propeller design, flight paths, altitude planning, and landing behavior will become part of the business model. A technically successful drone that society hates is not a successful drone. So what do next-generation drones really need? They need onboard AI that can make fast decisions without constant cloud dependence. They need multi-sensor perception that works in bad conditions. They need stronger energy systems and smarter aircraft designs. They need digital airspace integration for BV loss operations. They need cybersecurity against spoofing, jamming, and hijacking. They need redundancy and emergency behavior. They need explainable decision logs. They need quieter propulsion. They need modular payloads for different missions. And most importantly, they need a clear reason to exist. Because the future of drones is not about replacing humans. It is about extending human reach. A drone can inspect a bridge before a worker climbs into danger. A drone can deliver blood when traffic is too slow. A drone can find a missing person with thermal vision. A drone can map a wildfire before firefighters enter blind. A drone can check crops plant by plant, instead of treating an entire field the same. A drone can reach places where roads are broken, time is critical, or human risk is too high. But the winning drones will not be the ones with the most hype. They will be the ones that solve real problems with measurable reliability. The future belongs to drones that are boring in the best possible way, predictable, auditable, safe, efficient, and useful. The public does not need drones that look futuristic. The public needs drones that do the job and do not create new danger. The next era of drone engineering will be defined by one question: can this machine be trusted when conditions are no longer perfect? If the answer is no, it is still a toy, a prototype, or a limited tool. If the answer is yes, then it becomes infrastructure. That is the real future. Not drones as flying cameras, not drones as viral technology, not drones as noise in the sky, drones as intelligent infrastructure. Machines that inspect, deliver, protect, measure, coordinate, and respond. Machines that are smart enough to act, disciplined enough to stop, and transparent enough to be trusted. The sky above us has always looked empty, but the next generation of drones will turn it into a working layer of civilization. And the companies that understand this will not just build aircraft. They will build the rules, intelligence, safety systems, and trust architecture for a world where the air itself becomes a platform.